If you take exactly one belief out of this module, take this one. Data quality and lifecycle discipline outweigh the algorithm. Full stop. The line where you actually pick and fit a model equals random forest model.fit, is a couple of line of code that anyone can copy off the internet. That is genuinely the easy part. What separates a real working system from a demo is everything wrapped around that line. And here's the sharp, uncomfortable version that I want you to remember. A high capability model trained on poor inputs will lose to a simple model trained on carefully prepared features almost every single time. The fanciest neural network fed garbage will be beaten by a humble logistic regression fed thoughtful features. So we are going to spend our energy exactly where it pays off, on the data and the discipline, and treat the algorithm choice as the small decision it usually is. Let's start with the foundation, the three fundamentally different ways a machine can learn, and how you choose the right one for a given problem. Because picking the wrong paradigm is a mistake no amount of tuning can fix later. These are the three fundamental paradigms, and the honest truth is that the data you have usually chooses the paradigm for you, not the other way around. Supervised learning works from labeled examples. Every input comes with a known correct answer and it learns to predict that answer for new unseen cases. That's your spam detection, your churn prediction, your loan default risk, and your demand forecasting. Unsupervised learning has no labels at all. Instead, it discovers structure hidden in the data, clusters, grouping, anomalies, etc. That's useful for customer segmentation, topic discovery, and exploring fraud patterns. And reinforcement learning is different in kind. An agent takes action in an environment, receives rewards or penalties, and learns a strategy that maximizes reward over time. That's robotic control systems, dynamic recommendation, game playing. The key question isn't which is the most advanced, it's what does my data actually look like and what I am trying to do with it. A tell that helps in the room ask, do we have examples of right answer? If yes, historical outcomes, past labels, you're almost certainly in territory which is where the vast majority of business ML actually lives. If you have data but have no answers and you are hoping to discover structure, that's unsupervised learning. And if the problem is a sequence of decisions where each action changes what comes next, that's reinforcement. Powerful but far rarer in a day to day FDE work than the hype suggests. Let me make that concrete with three quick cases so the choice becomes obvious rather than theoretical. A bank predicting whether a customer will default on a loan. That's supervised because the historical records already contain the outcome. You know who defaulted, so you have labels. A retailer wanting to group its customer into behavioral segments that nobody defined in advance? That's unsupervised. There are no pre existing segment labels. You're asking the data to reveal them. And a warehouse robot learning to navigate efficiently through routes that keep changing? Reinforcement. It has to adapt through trial, feedback, and accumulated reward. Same lesson every time. Start from the business objective and the data you actually have in hand, and the paradigm names itself. Don't start from the technique you think is cool. Now, now that Now the step that in real deployments decide more of your final quality than the algorithm ever will. This is where the money is, and it's where beginners spend the least time. Pre-processing is the cleanup, handling missing values, standardizing your numbers, encoding categories, normalizing texts, duplicating. Take the slide again. Now, the step that in real deployments decide more of your final quality than the algorithm ever will. This is where the money is, and it's where beginners spend the least time. Pre-processing is the cleanup, handling missing values, standardizing your numbers, encoding categories, normalizing text, removing duplicates, dealing with outliers. Feature engineering goes a step forward. You build new variables that expose the signal more clearly than the raw data ever does. Raw timestamps become day of week, or hour of day, or recency. Counts become ratios and trends. For churn prediction specifically, engineered features like number of support tickets in the last 30 days, days since last login, ratio of active days to total days, and usage trend over the last 3 months will beat a raw table of individual events every time because they represent the actual decision context the model needs to reason about. And one warning that will save you from public embarrassment: beware of leakage. Never ever build a feature using information that wouldn't be available at prediction time. That is exactly the mistake behind our 98% disaster from the opening. A feature that secretly contained the answer. One more reason to start simple that people underrate is a simple baseline is a truth teller. If your logistic regression already hits 90%, a fancy model that reaches 91 is almost never worth the added complexity, the slower inference, and the loss of explainability. And if your baseline is terrible, that's telling you the problem is in the data or the framing, not the algorithm. So a bigger model would just be more expensive way to fail. Always earn your complexity. Only now, after the data is right, do we actually pick the algorithm. And I want you to reframe this as a context decision, not a prestige contest. The question is never what's the most impressive model. It's what fits this data shape, this need for interpretability, this latency budget, and this operational risk.